Okay, this is a place we're going to start. So some of you have seen many of these notes already, but we're just going to start from scratch and hit the high points. So we're in section 15.7. You have your definition of critical point on page 985, your definition of saddle point on page 985, and your second derivative test, which we're going to use, that's on page 986. Okay, but your second derivative test looks like this. We call capital D this determinant, and so the symbol there, the lines that look kind of, the two vertical lines, that's your determinant symbol. So of course you take your main diagonal, fxx, fyy, minus your secondary diagonal product, fxy, fyx. Now, D is an important number. It's going to help you with the determine if you have a max or a min. So if D is positive and the second partial derivative fxx is less than 0, then that means you have a local max at the critical point. If D is positive and that same second derivative is greater than 0, you have a local min at the critical point. If D is less than 0, there's a saddle point, which of course is neither a max nor a min. And if D is 0, then the test is inconclusive. So we're going to start with this one that we've already worked once, but we did it the long way. We didn't do it the short way, so the short way is going to be much more beneficial. So what we're going to do when we're determining extrema is we're going to take all the partial derivatives. So we'll start with f, the partial derivative of f with respect to x, and that of course would be 2x. And then we'll also take the partial derivative of f with respect to y, and that would be 2y. So that's how we need to start, and that's how we're going to find our critical number. So to find our critical number, we're going to take f partial derivative of x and set that to 0, and take f with the partial derivative with respect to y and set that equal to 0. Okay, so if 2x equals 0, then that means that x equals 0. And if 2y equals 0, that means that y equals 0. And so we have 0, 0, and that is a critical point. Okay. Now I don't know if that critical point is a max or a min, but that is our critical point. Now we worked this one in class before spring break, and we worked it by the theory way, but this way is just going to be quick and easy and to the point. Alright, so what the second derivative test told us to do was it told us to take all of the partial derivatives. So we're going to take fxx, which would be 2. We're going to take fxy, since there's no y there, it would be 0. We'll go down to this one and we'll take fyx, which would be 0, and then we'll take fyy, which would be 2. So taking our determinant is going to be, we'll have a 2 here, and a 0, and a 0, and a 2. And that determinant, remember you'll take your main diagonal, which is 4, minus your second diagonal, which is 0, and so you're going to get a value of 4. So what I know about that part is that D is 4, which means it's greater than 0. The second thing that I have to look at using my second derivative test is what fxx does. Okay, so here is fxx up here. So I know that fxx is 2, which is also greater than 0. So if D is greater than 0, and the second partial derivative with respect to x twice is greater than 0, then that means we have a local min at the critical point. And that's what it would look like. Now when I taught this in class before spring break, they put the z value in there as well, but I'm not going to ask you that. I'll just ask you for x and y. So that's what that answer would look like. Let's try another one. Alright, so the first thing we have to do with these is we find the first partial derivative. So we're going to take the first part, the derivative with respect to x. And so when we do that, we get 4x, no y's, plus 8, no y's, and no constant. Okay, we'll also take the derivative with respect to y, which would be 2y minus 6. And that's how we begin. So remember, to find the critical points, you're going to take 4x plus 8 and set that to 0. Okay? And you're also going to take 2y minus 6 and set that to 0. So you have a critical point at negative 2, 3. Alright, so now we're going to use our second derivative test. So let's take our derivatives. So we need to do fxx, that's going to be 4. fxy is going to be 0. fyx is going to be 0. And fyy is going to be 2. Okay, so D equals the determinant 4, 0, 0, 2. And this determinant is going to be 8. So D is greater than 0. I also know that fxx is greater than 0. So since D is greater than 0 and fxx is greater than 0, that means that negative 2, 3 is a min. That's how it would look. Okay, just checking my time for a second. Now then. So then we have this one. So we'll do the same thing again. The partial with respect to x would be a negative 2x. And the partial derivative with respect to y would be 2y. So we'll set negative 2x equal to 0 and 2y equal to 0, which means that x equals 0 and y equals 0. So 0, 0 is a critical point. Okay, so let's take our partials. Whoops, wrote it wrong. Haha. So obviously you see I made a mistake in the first one, so let's fix that. The partial derivative with respect to x twice would be a negative 2. That should be a negative 2 right there. Okay, so let's take the determinant. And we get a negative 4. Okay, so the determinant is less than 0. So if the determinant is less than 0, then that means that critical point is actually a saddle point. So we have 2 more left to do, but my time is running out on a 10-minute video, so I'm going to make it into a second video.